So the only restrictions we have are with division and with our square roots or even roots. The only thing we didn't write on our list, the only operation we didn't address is if we have an odd root. So when you have a square root, like the square root of 4, because the square root is the most common one that's used, they don't write the index, they call it, which is the little number that goes right there, which tells you which exponent that radical undoes. So the square root, they don't write the 2, and we know it undoes like something squared. But if there's a little 3 there, what that means is what number do you cube to get 8? So it undoes an exponent of 3 as opposed to an exponent of 2. So like the cube root of 8 is 2, because if you raise 2 to the 3rd power, you get 8. Does that make sense? And we'll talk more about those, like as far as evaluating them and simplifying them and stuff later on. But for now, it suffices to say that that little number in there is called the index of the radical. And if it's even, it behaves like a square root. And if it's odd, it's going to behave like a cube root. So the big problem with even roots is that you can't take an even root of a negative, right? Because you can't raise any number to an even power and get a negative number, right? However, what if I want to take the cube root of negative 8? Is there a number that you can multiply by itself, like 3 factors of that number, and get negative 8?
Negative 2.
Yeah, because if you multiply a negative times a negative times a negative, you do get a negative, right? So the problem with even roots is that that even number of negatives ends up being positive all the time. But an odd number of negatives can be negative, so the cube root of negative 8 is negative 2, which means I can take the cube root of negative numbers. So there are no restrictions on cube roots or odd roots. And again, you don't have to understand like a ton about radicals at this point. If all you remember is that odd roots are defined for all real numbers and that even roots have this restriction, like that's enough for now. We're going to talk a lot more about radicals as we move forward. But that's the piece of it that we need right now. Does that make sense? Okay. So let's do a few of these. Hopefully you messed with it over the weekend and used what we did on Friday. So let's start with find the domain. Let's start with f of x equals 2x plus 1. So if I were you, while doing homework, I would keep that list that we made on Friday, like in front of you. And when you see a function, the first thing you want to ask yourself is what operations is this function doing? So like on the right is the rule of what you're doing to your input, right? So this function is multiplying and adding. So then we look at our list at multiplication and addition. Are there any restrictions on multiplication or addition? There's not, right? So what's my domain? All real numbers. Good. And again, you can write that in interval notation too. I usually just use the shorthand because it's a lot of infinity. So let's do okay, what operations do you see now? There's division, addition. So On your list, you find addition. Are there any restrictions?
No.
What about division? Are there any restrictions?
On top, there's no restrictions.
Very good. So on the top, there's no restrictions, right? The only restriction is on the denominator, what you're dividing by. Your denominator can't be 0. So you could write, like you could be like, oh, my denominator cannot be 0. But that's always true, right? 2 is never equal to 0. So there's no x value that I could plug into this that would make 2 equal to 0, which means I can plug anything into it I want. Yeah? Stop me if you need clarification. So the domain here is also all real numbers. It's an ugly 3. Let's do g of x equals square root 5 minus x. Okay, what operations have we got now? Square root and subtraction. So on our list, we see subtraction has no restrictions. What about square roots? What are the restrictions here? I heard something about what can't be negative. Right, but what is under the square root, right? What we're taking the square root of can't be negative. So we're taking the square root of 5 minus x here. And if it can't be negative, that means it can't be less than 0, which means it has to be greater than or equal to 0. So like, we're literally just copying whatever is inside the radical and then writing greater than or equal to 0 every single time. Like, it'll never be a different inequality. But our domain talks about what x can be, and so we have to solve this for x so that we're getting values for x that satisfy this inequality as opposed to like values for 5 minus x. So we'll subtract 5 from both sides and divide both sides by -1. So we get that x is less than or equal to 5. And we're going to put that in interval notation. How are you guys feeling about interval notation? Is it like going well? Yeah.
Interval notation for all real numbers?
Yes.
Is always negative, infinity, comma, infinity?
Infinity, yep. Yep. What's it going to be for x is less than or equal to 5?
5 to infinity, bracket includes 5, comma, infinity.
Right, except the other way around,
It's a hard one.
because it's less than or equal to 5.
So
So yes, a hard bracket, but we want to go down. So yeah, so negative infinity up to 5. And if you find yourself getting tripped up about like which order it's in, there's a couple ways you can think about it. One is you could just draw a number line, like that I find really helpful. But also like you can think about like, is 5 the biggest thing or the smallest thing? Because in interval notation, the smallest thing's always on the left and the biggest thing's always on the right. So if you look at x is less than or equal to 5 and you're like, oh, 5 is the biggest thing, then that means 5 has to be on the right, and then you know that the infinity is on the other side. Oh, this is a good one. There was one like this on the homework. Okay, what do we see? Here, I'm going to change this actually to like a perfect square. Yeah, we see exponents.
we also see it's in the denominator.
Right, we see division, and there's addition. We don't really care about addition though, right? And exponents. Are there any restrictions on exponents? So what do we know from the division? That tells us what?
We can't equal 0.
What can equal 0?
Bracket and
The denominator? Yes, good. So x squared plus 4 is not equal to 0. And again, just like with the radicals, like this goes the same every single time. Like you copy the denominator and say it's not equal to 0. Like you don't even have to think through that part. As soon as you have a fraction, the denominator can't be 0. As soon as you have a square root, the radicand is greater than or equal to 0. And then from there, you'll have to figure out what all the sets mean, but that's a good start. So if x squared plus 4 were equal to 0, and we're solving this just like it was an equation, there just happens to be a line through the equal sign. So this means that x squared cannot be equal to negative 4. What do you think? Yeah. So there ends up being no restriction here because x squared is never equal to negative 4, right? If you square a number, you always get a positive because a negative times a negative is a positive, and a positive times a positive is a positive. So x squared as a value itself is always positive. Well, greater than or equal to 0. It can be 0 too. But it's never equal to negative 4. There's nothing I can square to get negative 4. And so there's no restriction here. Does that make sense? And so the domain is, again, all real numbers. Okay, let's do a couple more. Trying to think of the funny ones so we can have a look at them. Let's do f of x equals the square root of x plus 5 over x minus 1. Okay, so I immediately see that I have a square root and I also have a fraction, right? And so like what that tells me is that I'm going to have two different conditions I have to satisfy. So you kind of want to just address them separately and then you can put them together at the end. So because there's a square root, what does that tell me? What's it?
The radicand?
Yes, good. The radicand is greater than or equal to 0. So the reason I'm bugging you guys about saying the word it is because if we get in our head, like, it can't be 0 and it has to be greater than or equal to 0, like, we think that we'll always remember what it means, but it's really easy, especially on ones that have no restriction, to, like, grab an it that you don't need to, like on number 2, making 4 plus x not equal to 0, for instance. So if you can, instead of it, if you can think of denominators can't be 0 and radicands have to be greater than or equal to 0, then in your head you've got it a little bit more specific so that you know what you're seeing every time. So we have our radicand is greater than or equal to 0, which means that x is greater than or equal to negative 5. And then what else do we see? What can't be 0?
The denominator.
Yeah, good. So our denominator, whatever it happens to be, cannot be 0. So that means that x cannot be 1. So now we have to worry about how to put these together to make a single set. I think probably the easiest way to do that is just to look at it on a number line. So I know that x cannot be 1. So I can put like an open point at 1. And then I know that x has to be greater than or equal to 5. So far so good. What about on the other side of 1? Are those numbers greater than or equal to 5? So, and then you can use your soft brackets if you want to see, so you can see what it'll look like in interval notation. So really, like, this one is just like one where it's everything but 1, right? We did that the other day. So everything less than 1 and everything greater than 1, except instead of going all the way down to negative infinity, we're only going down to negative 5. So it's all real numbers that are greater than negative 5 except for 1. So we'll need a union here because we have to skip a value. So -5 up to 1, and then 1 up to infinity. I really encourage you guys to draw number lines on these if you have any trouble with the interval notation at all. It really does help to just visualize it a little bit. Okay, you guys want to try one? Oh, did everybody get this on Friday? I know a couple people were gone. If not, you want to like take a picture right now if you were gone. It might be helpful. Good? Okay, give this one a try. What number are we on? 6? Yep. And we also know that our denominator cannot be equal to 0. And it's true that if the square root of x plus 2 were equal to 0, that would mean that x plus 2 were equal to 0. So you can essentially just drop that square root. And so let's see, x is not equal to -2. And x is greater than or equal to -2. Okay. Here's the question. What's up?
I don't get how you got the left.
The one on the left?
Yeah.
So anytime I have a square root, whatever is underneath the square root or inside the square root has to be positive. It can't be negative. So regardless of where the square root is, like in the expression, anytime I see a square root, I'm just going to take whatever's under it and set it greater than or equal to 0 every single time.
And that's what you do on the right, isn't it?
Well, on the right, I set the denominator not equal to 0. So this is because I have a square root, and this is because I have division. The thing I'm dividing by can't be 0, and the thing I'm taking the square root of has to be positive. Yeah, this one's tricky because they're both like the same thing. So here's the big question. If x has to be greater than or equal to -2, but it's not equal to -2, forgot my slash, then what does that say about x? So the one on the left gives us two options. Either x is greater than -2 or x is equal to -2. Then the one on the right says x is not equal to -2, leaving us what? X is greater than -2, right? That makes sense? Mm-hmm. So all it does is this. Because that greater than or equal symbol, it doesn't mean that it's like both greater than and equal to. It just means that whatever number x is, it's either greater than -2 or it's equal to -2. And so the one on the right says, well, that's nice, but it can't be equal to -2. So the only option left is that it's greater than -2. And so our domain is going to be -2 to infinity. And this time we're not including that -2 because it was in the denominator is what got rid of the hard bracket for us. You guys want to do one more? I'm not done. Oh. What do you guys think? Mm-hmm. Yeah, the only operation here that has a restriction is the division, right? Because that's a cube root. It's got that little 3 in the little nook. If that little number is odd, then there's no restriction on what can be inside that radical. So the numerator doesn't have any restrictions. And then we just have division here that says that we can't divide by 0, right? So x plus 9 cannot be equal to 0. So if x can't be -9, that means that x can be anything under -9 and anything over -9, right? So when we do the domain for these ones, it's really like we're doing like two separate sets, right? We have x is less than -9 and x is greater than -9. So -infinity to -9. And then -9 to infinity. And I know that kind of looks like we didn't skip anything, but remember those soft brackets mean we got infinitely close to -9, but we didn't actually reach it. And that's on both sides. So like the only thing we've skipped is -9. So these take a bit of practice. Like you got to go through a bunch of them to like really start trusting yourself. But what I would do is take, like when you do your homework, like put this list in front of you and really like in your head just list all the operations and find them on this list and be like, oh yeah, there's this restriction. And if you do it methodically like that a bunch of times, you'll start to feel, I think, pretty confident about it. Good? Okay. So I printed out today's notes because there's lots of graphs. So we did a bit with graphs on Friday. Today we're just going to kind of extend that a little bit more. This particular one has an application attached to it, so we can see like how to go back and forth from the graph to the application. So let's just start with domain and range. What's the domain of this function? So yeah, the domain is the set of all possible ages. That's right. So numerically, what is it? What range of numbers is it? What's the youngest age?
5.
0 to 20.
Yeah, 0 to 20, Lily. I think you're just looking at the range. So 0 to 20. And again, I'm including both those endpoints because I don't have an open point. So if there's not an open point, we assume that that point exists. And then the range, Lily, what's the range? You said 5 to...
5 to 1.
Yeah. And there's a little bit of estimating on these. I'm not going to be super strict about that last number as long as it's between like 120 and 130. Okay, so we want to know what Sue weighed at age 5. So what that's asking, it's giving us the age, and it's asking us for the weight, which means it's giving us the x value and asking for the y value. So that's equivalent to us evaluating the function w for an input of 5. So what is w of 5?
40.
Good. We could say 40 pounds up here. So if I were to ask you for w of 5, it's the same exact question as what did she weigh at age 5? And then we want to know what ages she weighed 90 pounds. Now notice when we give you this one symbolically, that the number's on the other side. Like that's how you know if you're looking for the x or the y value. So we can think of, I always think of this statement like w of x equals y. So if they give you this number on the right side, they gave you what y is, and they're asking for x, as opposed to the previous problem where they gave you what was in parentheses, that's your x value, and they asked you for what it's equal to, which is your y value. So at what ages did she weigh 90 pounds?
12.
Good. So our output, or our y value, is 90 for an x value of 12. Now we want to know what ages she weighed no more than 80 pounds. So we're looking for where y is less than or equal to 80. So notice again this notation. There is no number in the parentheses, so we're looking for x values. And we're saying that our y value is less than or equal to 80. So what ages would that be? Good. And I'm going to include the 11 because that's when she was 80 pounds. And my inequality is the or equal to variety, right? So I'm including where her weight was equal to 80. If this hadn't been there, I would have a soft bracket at that 11. Okay, let's talk intercepts. So in general, the vertical axis is our y-axis, horizontal axis is our x-axis, and intercepts are just where we cross those axes. So the y-intercept is the point where we cross the y-axis. The x-intercept is the point where we cross the x-axis. So looking at this graph, I see that there's no x-intercept. You guys see that? Why does that make sense in terms of this problem? What does it mean?
Can't weigh anything if you don't exist.
That's true, you can't weigh anything if you don't exist. But if you do exist, you have to weigh something, right? So the weight can never be 0, which is what it would mean if we were on the x-axis, right? Our y value would be 0. And so that's impossible. What about the y-intercept? What's the y-intercept? I think you all have the right answer in your head, and you're all afraid to say it. Are you looking at this point right here? Yes, that is the correct point. I'm going to call it 5, only because we called it 5 up top when we did the range. But again, I wouldn't be super picky about where exactly you were on there. What does that mean in terms of this problem? What does that 0, 5 tell us? Yeah, it's her birth weight, right? When she was 0 years old, so when she was born, she weighed 5 pounds. So birth weight was 5 pounds. 10 might have been a little healthier. Okay. So now we're going to do the same thing. We're just going to take the application out of it and just do it symbolically. So again, we want domain range. I think I'll let you guys do this one. And we'll do the next one together because it's got some funny ones on it.